The following is my conversation with Dr. Jason Rolfe. He is the co-founder and CTO of Variational AI. Variational AI uses machine learning to rapidly generate novel compounds that are optimized to increase the clinical probability of success. Jason has previously worked as a machine learning researcher at the world's first quantum computing company, D-Wave. Some of you may remember that Jordy Rose, D-Wave's founder, was our first ever guest on this show. Jason has a PhD in computational and neural systems and has done research at many of the world's top universities, including MIT, California Institute of Technology, and New York University. In our conversation, we talk in detail about how AI works, starting with a non-technical overview and then diving deeper into the complexity of the systems they use for drug discovery. We then talk about the kinds of innovations AI will soon bring and the kinds of job disruptions that will follow alongside them. Jason talks about the hard skills and aptitudes we must develop to thrive alongside AI, as well as practical recommendations for where and how to best learn machine learning concepts. I found Jason to be an extremely generous person with a spark for science and learning like nothing I've ever seen before. I hope you enjoy this conversation as much as I did. So why don't you begin with telling us a little bit of the overview of your career to date and the founding journey at Variational AI?
Okay. I've been studying machine learning for over 15 years, specifically generative learning. I actually started my graduate career in experimental neuroscience, which didn't really agree with me. I didn't enjoy all of the lab work, specifically working with rats. So I transitioned to theoretical neuroscience, spent most of my PhD looking at biologically plausible machine learning algorithms, trying to identify machine learning algorithms that are consistent with the neural architecture of the brain. I did my postdoc with Jan LeCun, who's well known at this point in the machine learning community, and started working on, I guess, deep learning sorts of things at that point. After my postdoc, I spent maybe 7 years at D-Wave Systems, where I progressed to principal machine learning researcher, worked on algorithms that were consistent with the architecture of a particular sort of quantum computer, a adiabatic quantum annealer, as well as, so that the algorithms that I developed there used variational autoencoders with they were designed so that the prior of that variational autoencoder was consistent with the computation performed by the quantum computer. So that developed a potential application for the quantum computer, and then transitioned to trying to develop practical applications of that algorithm. So what can you do with a powerful variational autoencoder that would actually be of commercial or industrial interest?
What were some of the applications that you came up with?
I worked on a number of applications within bioinformatics, cheminformatics, industrial process control. We attempted to develop a number of different industrial applications, which we were working towards selling, but eventually D-Wave decided that it didn't want to have a machine learning division anymore. It needed to focus entirely on developing the quantum computing hardware. So it disbanded the entire machine learning group.
Wow.
At which point I and a number of my former colleagues came together to form our current startup, Variational AI, where we're attempting to use generative machine learning in order to accelerate small molecule pharmaceutical development.
Wow, that's fascinating. It's interesting you mentioned D-Wave because one of our first podcast guests was Jordy Rose, founder. So it's interesting. It's kind of a small tech space in Vancouver. Everything kind of overlaps. It's interesting.
Yep, Jordy was my original supervisor at D-Wave. So
wow. So why don't you tell us a little bit more about how you use AI? Some of our listeners aren't technical at all, so maybe kind of an overview, not super technical, and then maybe you can dive a little bit deeper.
Okay. We are absolutely a machine learning first approach to drug discovery. Generative machine learning, as I assume most people are aware at this point, but I'll try to give a very sort of high-level technical summary. The basic idea is that you want to model the probability distribution of some domain. So the sort of domains where this is most well known at this point are in the language domain with large language models, where you're trying to learn what is the effectively statistical structure of natural language. One of the defining aspects of a generative model is you're able to draw samples from that distribution. So drawing a sample from the probability distribution of natural language would correspond to a well-formed syntactically and semantically sentence in English or whatever language you've trained on. This is also done commonly in the visual domain. And in that case, when you draw a sample, you get a photorealistic image. We are applying generative modeling over the space of drug-like molecules. This is qualitatively different than either vision or natural language because of you can call it the topology of the objects that you're generating. In images, you're generally producing a grid of pixels. One pixel, you need to set the RGB values of each pixel in a square grid, and that gives you your image. For text, it will be a sequence of, usually they're word part tokens. People generally don't use character level language models. They don't use word level language models. They divide things into word parts, which are somewhere between characters and full words. But you need to produce a sequence of these tokens, which then come together to form a series of words and a series of sentences and eventually paragraphs and the full answers that you're getting out of ChatGPT. Small molecules, in contrast, don't fall on one of these sorts of regular grids, either linear or square. They are best understood as graphs, where the nodes are atoms and the edges are the bonds between the atoms. The topology of these graphs, they can be sequences, linear sequences, they can be trees, they can contain loops, they can have interconnected loops. And you need to build a system that is able to effectively work with that topology. Whereas, any sort of convolutional architecture, traditional convolutional architectures are designed specifically for square grids or linear sequences. So that requires a different approach.
To take a brief tangent, I'm curious, like, what your thoughts are on technologies like ChatGPT. Some people are like, there was I think an employee at Google or DeepMind who was thinking it's completely conscious, and what's your take on like the philosophy behind it? Like, do you think it reveals something fundamental about the human mind, or do you think it's just a cool kind of toy party trick type thing?
So my feelings on this are informed by the years that I spent thinking about the human brain and its relationship to machine learning algorithms. I think that consciousness is mostly a distraction, that there is no deep problem of consciousness. Consciousness is as consciousness does. Something that appears to be conscious actually is conscious. What we perceive as our qualitative experience is the nature of a system that is doing the sort of information processing necessary to appear intelligent within the world. Any system that appears intelligent is actually consciousness. It is actually conscious. There's no magic to the neurons in our brain as opposed to the transistors in a computer. There's no, special quantum effect that then enables connection to some sort of immaterial soul. And philosophers frequently take this in, I think, rather surprising directions that are not consistent with reductionistic science. And I firmly believe in the Enlightenment program of understanding the world by decomposing it into its parts. But ChatGPT is, as far as I understand it, not yet sufficiently sophisticated and complicated to rise to the level of human intelligence, and thus I don't think it possesses something like human consciousness. I'm not an expert with ChatGPT, but my understanding is that, for instance, it doesn't necessarily preserve state as well as a human would over the course of long blocks of text. So what gives us the manifestation of a consistent mental state in us is the expression of that is our ability to maintain a consistent line of thought and a consistent perspective throughout a long interaction. And to the extent that that isn't present, you have something that's more like the consciousness of goldfish rather than a consciousness of a human.
Mm.
But I'd be happy to believe that ChatGPT has consciousness comparable to a goldfish.
That's yeah, that's what I was gonna say. Like it's interesting. Like if we're comparing it to humans, obviously it's not quite there, but if you compare it to like a horse or something like that, it starts to get a little bit closer.
Yep.
That's fascinating. Yeah, the other thing I was going to ask is how has technologies like the large language models and the diffusion models for images has that changed? Because you founded Variational AI in 2019, kind of before all the hype has been around AI in the public media. Has that shifted the way you guys work at all?
We change our algorithms and evolve our algorithms as new approaches become available that appear to be relevant to what we're doing. Um, we have not been significantly influenced by large language models, although, transformers are a fantastic and effective architecture, which everyone should be conversant in. But large language models in particular are trained on large amounts of natural language, whereas we are specifically interested in small molecules. What makes a molecule synthesizable, what makes it stable, what makes it an effective inhibitor of various proteins within the body. And that is dealt with in the corpus of language on which large language models are trained in only the most tangential and indirect way.
Mm.
There are, of course, some chemistry texts in those corpuses. If you ask a large language model a question about chemistry, it will construct an answer for you, but I have seen no evidence that it has knowledge comparable to a medicinal chemist who has spent years explicitly studying this. Until it's better than a medicinal chemist, you're better off actually hiring a medicinal chemist. The economics of drug discovery are rather different from the applications where a large language model would be effective presently. Right now, those applications are ones where a large amount of human interaction is required, which doesn't need to be especially precise because it's not essential that those interactions be exactly correct, and they're not depending upon very sophisticated knowledge and reasoning processes. So, you could use a large language model for customer support applications. In contrast, for small molecule drug discovery, the cost of doing the wet lab experimental work to confirm any hypothesis is exorbitant. To synthesize and test a novel small molecule is on the order of thousands of dollars, and you're going to have to go through thousands of different molecules as you progress to a final drug candidate that can be entered into clinical trials. So you're not trying to save pennies on the selection of the compounds. You want to invest as many resources as possible into, as quickly and efficiently as possible, converging onto a successful drug candidate. The costs of the experimental work to verify that, again, are overwhelming. And then when you enter into clinical trials, that's where the real expense comes in. And you want to be extremely confident in your candidate as you enter clinical trials because those cost, I would guess, on the order of hundreds of millions of dollars to run a full clinical trial through phase 3. We work on much earlier stages than that, and I handle the machine learning side rather than the business side. So I couldn't quote you the exact cost of a clinical trial, but they're overwhelming.
Wow. What do you see as like the timeline and like the rate of progression over the next like 10 to 20 years? Like how do you see AI working in the medical field in the next little while?
I will agree with many other people in the field that I would not want to be a radiologist in training right now. I think the career of radiologists there will still be radiologists 10 years from now, most likely, but a large fraction of their workload I expect will begin to be taken over by automated systems due to regulatory concerns, due to politics, due to psychology. It will take time before people become comfortable with a machine delivering a final diagnosis. There's also the question of who is legally liable when inevitably mistakes are made. But my understanding is that there are already cases where there is at least evidence that the machines are the ML algorithms are at least as accurate as the average human. So I expect in diagnosis, especially in the more image-based diagnosis domains where you're looking at a CT scan, for instance, I expect there will be a massive impact of machine learning algorithms within the coming decades.
And on that topic, what other jobs do you think, like if you had to put into a few different categories, like you're definitely safe in one category, you're definitely screwed in the other category, and then there's kind of like the middle ones. Are there some jobs that are like you should definitely be like, because most of our audience is university students kind of trying to figure out where to go with their career paths. Like, is there anyone where it's like you should definitely turn around and try something else? Or and are there some like you're definitely going down the right path?
It's an interesting question, and I want to concede my own fallibility in the predictions that I'm about to make. Had you asked me 5 years ago if large language models would be able to write correct and effective code in the near future, I would have said no. I continue to find their efficacy in producing computer code surprising, given how difficult it is to specify what you want a piece of code to do unambiguously to a human. Just describing the objective for a coding project precisely so that it is impossible to interpret incorrectly is challenging. It requires, in some sense, the code is its own documentation at the most precise level. There's also huge amounts of sensitive interdependence within a piece of code. The distribution of correct programs given a program specification is ridiculously multimodal. You can arbitrarily change a variable name, and so long as you consistently change that variable name everywhere else, it's perfectly acceptable. You can implement your loop with iteration versus recursion, and either implementation decision is fine so long as you do it consistently. These sorts of that corresponds to long-term dependencies, which if you go back before transformers to recurrent neural networks, those sorts of long-term dependencies were a real difficulty, a real challenge to get networks to model and respect. So I would not have predicted the success of large language models in becoming coding assistants. And I don't think anyone expects that programmers will be replaced entirely. If you look at the transition from early programmers writing assembler or machine code to the early compiled languages to something like Python with the massive libraries and frameworks that are available to it, the task of programming today would be unrecognizable to someone who learned how to program in the 60s. So there's been massive evolution there, and yet there are more programmers than ever. I'm sure that large language models will change the way in which people program. Probably there will still be programmers. Will there be as many? Will this decrease the need for programmers because each programmer becomes so much more efficient? Or will it just mean that there are new domains in which it is now economical to invest in writing code and trying to automate processes? That's a question that requires a fairly detailed knowledge of the domains in which these things would be applied. And like you look at the evolution of social networks, which have created new sorts of human interactions with computers, opened up new economic domains in which programming would be useful. I think it's difficult to predict where that's going to go. There are certainly examples from history in which the evolution of a new technology has completely gutted an industry. The number of farmers today, the percentage of humanity engaged in agriculture today versus before the Industrial Revolution went from like 80% to under like 5%. It was a massive change. The number of people in the industrialized world engaged in manufacturing has decreased substantially. over time, and people have moved into more services-based economies. So there's certainly a risk there. Which particular industries are going to be upended? I'm not sure.
Is there kind of a roadmap for anyone? Like some people say depth is important, like have a very deep understanding, and then even if you're not going to be writing the code, you'll understand how the entire system works, and then you can implement the new systems. Like, is there any general advice that you have when kind of navigating a future with lots of automation coming um, for students?
Thinking about the way in which economies and jobs have evolved over the preceding decades, I think maybe my personal philosophy, my personal approach is one of flexibility. That you can't assume that the particular job that you are taking immediately out of graduation will exist 20 years from now, let alone 50 years from now. You probably expect after graduating from undergrad to have a career that's going to span roughly half a century. I think it's unlikely that any job that you pick is going to exist in an unchanged form over that period of time. I think that people need to expect that they will be forced to evolve, if not entirely reinvent their professional lives over the course of those 50 years, which is scary. But if you know that going in, it affects your choices, it enables you to choose more rationally, and it perhaps reduces the psychological shock when things do change.
What do you think are like the qualities you mentioned flexibility that the people who are going to succeed the most alongside AI in the future?
I think you need to always be learning. I think that you cannot assume that the skills that you have developed are sufficient to support you into the future, and you need to constantly be advancing your skill set, adapting to new technologies as they arise, building new skills in adjacent areas of knowledge and industries in order to maintain that flexibility.
To talk a little,
Graduated 20 years ago in computer science and was an expert in Java, writing the sort of backends for web pages that existed 20 years ago. That job doesn't exist anymore. The world has changed even since then.
well, do you have any specific advice when hiring software engineers and sorry, not for hiring, but like for us when we're applying for jobs, things like software engineers and data scientists? Like what do you think the best approach if we want to get hired at the top companies is?
I don't think I have a good answer for that, in that I'm usually looking for people with research experience, because what we do is fundamentally research. And that is a extremely difficult skill set to develop over the course of 4 years of undergraduate education. A PhD is basically a 5 or so year apprenticeship program in which you get thrown into the deep end and need to figure out how to effectively operate within a bleeding edge domain that can't be taught through coursework. A PhD, you're paid very little, and the benefit for that is you are allowed to work in a domain where you're out of your depth and develop those skills, which then presumably serve you well in whatever you're going to do next. So I'm generally looking for people who have developed that skill set, which again is very difficult to develop as an undergraduate. The other skill set which I'm skeptical of the ability of an undergraduate education to provide is the ability to work on large industrial code bases. So there's a real difference between writing a 500-line piece of code and writing a 50,000 or 500,000 line piece of code. Especially, I mean, at that point, the code is so large that you cannot hold the entire thing in your head at once. And the sorts of abstraction techniques and architectural techniques that you need to use in order to make the code, keep the code understandable and maintainable. They're just not necessary when you're working on a smaller scale piece of code. And that is, it's a skill set which I think would be difficult to develop unless you were working on those larger pieces of code.
How do you recommend we develop that? Is there any way to do it while still in undergrad?
I can't really speak from experience to that. I would guess that if you were able to contribute to, for instance, a large open source coding project, a large open source coding project is an instance of that sort of large software infrastructure where you need to maintain very careful abstraction barriers, you need to have very clear interfaces, you need to have very aggressive unit testing in order to make sure that each piece works, because you can't just test the entire finished product and be confident that you're going to have sufficient coverage. All of this becomes much worse in the context of machine learning, because writing unit tests for machine learning is often all but impossible. You don't know how each individual piece is going to work. You don't even necessarily know how the entire thing should work if you're operating in a research context where you're trying to develop something new. You have a vision of how you want the overall system, how the overall system should work. But even if you've correctly written each component of it, if your hypotheses about the necessary architecture were incorrect, the code can be perfect, can be exactly realize what you specified, and yet not achieve the desired goal. I sort of drew that out in a tangent. But yeah, experience with large code bases and working in a team, the more you can gain in that, I would think the more hireable you would be.
Going back and kind of looking back over your career as a whole, like how do you have any advice for figuring out what your passions are, and like do you have a framework for making your decisions on what opportunities to take? I think a lot of young people struggle a lot with deciding, should I do this or do that, or how do you approach those kinds of problems?
I think it's very difficult to know what a particular career will be like if you haven't actually sampled it. The day-to-day work of a job is often not what you'd imagine it to be from the outside. There are tedious aspects which aren't highlighted in the promotional materials, for instance. So if you can get an internship or some other sort of hands-on experience with the actual career that you're considering pursuing, I think that that is invaluable to making an informed decision about what you want to do. I think universities are really terrible at facilitating this. They have very inwardly focused, and professors know what it's like to do academic research in a domain, but the typical professor has never worked in industry. That's not the career path. You go undergraduate degree, PhD, postdoc, depending upon the domain, in biology, often many postdocs, and then you try to get a tenure track professorial position. At no point do you actually go out and see what the industrial side of that domain is like, which puts you in a very weak position for advising and educating students to enter the industrial world, which isn't to say that you aren't getting a world-class theoretical education, but in terms of career advice regarding what job would be suited to your personal dispositions and capabilities, that's not necessarily the sort of thing that your professors have a lot of personal experience with, that they'd be able to give you nuanced advice. Informational interviews, I think, can be very effective. Contact someone who is in the domain and basically ask to be clear up front. You're not asking for a job, you just want to pick your brain. And it's often very flattering to be asked what you think about an industry. And people will often be open to that.
I'm curious, like, what is your kind of how would you divide your energy at variational AI? Like, if you say like 30% is this, 20% is this, how like what does like an average week look like in your life?
So at this point, I'm a chief technology officer, which means that I am very responsible for many of the business sides of things, or interfacing the business considerations with the technical considerations. So the part of my job that I enjoy most is trying, often unsuccessfully, to stay abreast of the literature. At this point, I read as much in chem informatics as I do in machine learning, which I think is not as rich technically. I don't enjoy reading those papers as much, but I need to know the domain, the application domain, as well as the fundamental technologies that we're applying. If you don't know both, you're going to devise a rather inefficient and suboptimal system. I spend a lot of time speaking with the people who are actually doing technical work, trying to work with them in order to help them refine their approaches, provide a sanity check on what they're doing, provide an outside second perspective, coordinate all of their efforts in order to make sure we're all pulling towards an efficient common goal. But I also spend a lot of time trying to raise money from venture capitalists and interfacing with our customers, and doing the work that no one else has yet done in order to support a customer deliverable. Yeah, so there's a lot of business side work as well.
What about on like the data science side? Like, what would a data science person like? Is a lot of their work like cleaning the data, or what is like the breakdown there? What do you say?
We do at this point have one person who's effectively a data scientist. Most of the people on our team are either machine learning researchers or computational chemists or chem informaticians. There's a lot of data cleaning work required in the pharmacology domain. The data sets that exist, or the databases that exist, are often rather error prone. So the ability to the extent that you can identify erroneous data points or even correct them based upon the original source data from which the database was aggregated, this is invaluable. Obviously, any sort of manual correction effort is extremely labor intensive, and in the limit would imply the entire reconstruction of the database, at which point, you should have just built it yourself from scratch. But that is an enormous undertaking and not feasible. So yes, we do some data science work, but most of our work is more on the machine learning research side, or using chem informatics and computational chemistry techniques to construct additional data.
We talked a bit about the future of AI in medicine the next little while. What do you see as like the major progressions? Like if we look back, we look at the Industrial Revolution and things like that. What are those next few steps to come? Like in your mind, just like I know it's hard to make predictions, but just what does your instinct tell you?
If you're asking about medicine as a whole, I think that there are multiple different subdomains within medicine, and the application of machine learning to those is going to be largely independent. So we spoke a bit about imaging diagnostics, and I think there's a reasonably straightforward pathway for applying the sort of techniques that have been developed in the academic machine learning community to those domains. A large part of the challenge there is almost regulatory. The data sets tend to be extremely inaccessible. They're siloed within individual medical providing institutions, like an individual hospital. They're subject to extremely strict privacy laws, which makes it difficult to access that data, let alone aggregate it into a unified data set on which you could train a large model, like the sort that are trained on, ImageNet is not the training set at this point. There are much larger image data sets, but that's what you would want, and then you'd want to apply those sorts of architectures. But the challenge there is not so much on the ML technical side, it's domain-related regulatory and logistical issues. You might imagine applying machine learning to other diagnostic tasks that are not as imaging based. You have the full health record of a patient, and you want to see if there's an underlying diagnosis that previous clinicians have missed. That would be a natural sort of task. A lot of that data is in free-form text, which large language models are a natural tool to apply, but it's also very multimodal in that you're going to have both the free-form text and lab results, which will be, tabular numeric data, as well as imaging-based results from MRIs or CT scans or whatever other diagnostics a person has had. That's another interesting domain in which I think there's been some progress. There are efforts to roboticize surgery. I'm going to forget the name of some Renaissance Italian name. There's a robot in commercial use today for surgery. So you can imagine that will certainly progress as time goes on. And there's obviously a huge opportunity to create new therapeutics, both small molecule pharmaceuticals, as well as antibodies and other diverse approaches, or vaccines, obviously. Especially like an mRNA vaccine, it's easy to imagine how you could apply machine learning to selecting the sequence of the base pairs within the mRNA that's being delivered.
On a bigger scope outside of just medicine, like do you have timelines in your head for things like AGI, or like what do you see as like the biggest like societal shifting implications of AI in the next 20 to 100 years?
Well, I think AGI, if and when it is developed, will change everything. That will be a sea change, the effects of which I think are very difficult to predict from the outside. But if you have machines that are, once we have machines that are almost as intelligent as humans, it's easy to imagine how they would quickly progress to things that are more intelligent than humans. At which point, I think the real question becomes, what do you mean by human? If we're interested in human culture and the evolution and continuity of human culture, I see no reason why that couldn't be continued on a silicon substrate. Humanity cycles every 80 years or so. We don't perpetuate ourselves as individuals. We perpetuate ourselves through our children and future generations. What does it mean to have a child? People have biological children, people adopt children. I would guess that at some point there will be a generation of children that are not carbon-based.
Wow. How do you think about that as a scientist and as a human? Is there a distinction between the two? Like, is there a part of you like I've heard scientists say, I think this with my brain, and I think this with my heart. Is there kind of a distinction for you, or do you kind of have a unified perspective on it?
I think my brain and heart are reasonably well aligned in this.
It's interesting. Do you have any general advice for young people throughout university on career or just life in general, ways to spend our time or to look back and feel fulfilled after our undergrad and our life in general?
I'm not sure if I would trust my advice in this regard. I think that the particular questions that you've already asked were good ones. How do you select a career? How do you maintain yourself within that career as the career changes underneath you? You can never be too informed about the decisions that you're going to make. It's very easy to not be informed, especially during your undergraduate education, because you're ensconced within this protective institution that constructs a culture which is not the same as the culture that you'll be facing after you enter the working world. And you're being forced to make decisions now, not knowing the world in which those decisions are going to play out. So the more you can know about the world that you're going to be facing after you graduate, the more responsive you can make your present decisions. I've always found it surprising how common the advice is given to undergraduates to follow their present passions, that a university education should be for its own sake. It's not technical training for future employment. you're going to spend, again, roughly 50 years in your chosen profession. I mean, unless artificial intelligence upends everything and human labor is made irrelevant and everything is replaced with universal basic income and we all sit on our couches watching television while the robots do all of the real work. But assuming that isn't going to happen, or preparing for the time until it does happen, you're investing 4 years of opportunity cost that you could have been doing something else, as well as a non-trivial amount of actual money into making yourself best able to follow the course that you will want to after you graduate. And I find it almost disingenuous when a 18-year-old is advised to, I'm probably going to say something that's not entirely politically correct here, but major in comparative literature or major in philosophy because they find it intrinsically interesting. Like, there certainly is something to say for the life of the mind and, furnishing your mental space so as to be rich and interesting to enable you to lead a full and fulfilling life. But I don't think it is wise to do that at the expense of preparing yourself for a rich and fulfilling career.
One of the questions I like to ask all our guests is, looking at your life, is there any like underpinning habits, like daily practices? It could be as simple as taking a cold shower or things like that, that you just think make like a huge difference in your life. Like obviously there's so many habits we do. We have to-do lists, we have all these things, but are there any specific things that you think make like a massive impact on your life that you do?
It's difficult. The rest of your life becomes much more challenging if you are not in reasonable physical condition. So daily exercise and maintaining a healthy diet, getting enough sleep, I think that these are all very wise things. It's easier to skimp on those things when you're younger. Your body is just more resilient. But developing the habit of exercising every day, eating well, sleeping reasonably well, I think that will serve you well into your future.
Okay, so last two questions. The first is, are there any tools that you use, whether it's different apps or Chrome extensions and things like that, that have been tremendously useful for you as well? Just fun things that you think we might be interested in.
My favorite thing on the internet is Google Scholar.
Google Scholar.
The ability to chain back and forth through references, especially being able to see the the papers that cite a paper rather than the papers that are cited by a paper, is incredibly useful. The machine learning literature has exploded over the course of the past 20 years. If you go back to the early days of NeurIPS, back when it was just NIPS, everyone knew everyone. You could see all of the posters in a poster session. The field was relatively unified and everyone was sort of a Renaissance person. Everyone had some sense of all of the major work that was going on. Today, that is impossible. There's just too many subfields, each of which is too deep and rich and extensive for any one person to follow everything. It's very important to focus your efforts on the most impactful pieces of knowledge. Most papers do not stand the test of time. Most papers are irrelevant. There is a small fraction of the papers produced in any given year that end up being impactful. So focusing your efforts on those impactful elements, I think, is very useful. This is probably less relevant speaking to undergraduates rather than graduate students. You're probably spending less of your time reading papers. But there are 50 papers from the past 20 years that have had a massive impact. And reading that particular set of 50 papers, that's giving you a good foundation for moving forward.
Is
If
there
you
a way
picked a random papers, it would be worthless.
is there a way to easily vet those papers and find the most effective ones to read?
It's most obvious the older they are because they'll be the ones that have 10,000 citations.
I see. And then the last question is, it can be papers, it can be books, it can be movies, just any resources that you think we should definitely check out that are either interesting or beneficial, or websites, courses, anything like that.
Um, there, so again, I think Google Scholar is an incredible resource. There was one textbook that I used early in my machine learning education, which I found gave me a very interesting perspective. I'm not remembering the title, but can you give me a second and I'll pull it out? Can you put a gap in this podcast?
Of course.
I'll be back in one. David Mackay's Information Theory, Inference, and Learning Algorithms.
Perfect.
Um, it's definitely not deep learning. This is it's an information theory perspective on machine learning, which I thought was fascinating at the time. I continue to think is very interesting. It's the sort of thing that would build your wider perspective and your intuition rather than giving you particular tools and techniques that you'd want to apply today.
Awesome. Is there anything else that you think we should point our attention towards?
There really don't exist great textbooks for more modern machine learning topics. I think the field just moves too quickly. So, Ian Goodfellow wrote a textbook on deep learning. I think it's getting almost back 10 years now, which at the time was impactful and heavily cited, but the world has just moved on since then. It's very difficult. By the time you finish writing a textbook, there is already some new hotness that everyone is devoting all of their attention to. But again, there are these seminal papers which have an outsized impact, which are heavily cited, and which I think it really is advantageous to read.
And in terms of learning, are there like courses or resources where you think we should spend our efforts? Like there's a whole host of online courses, but are there any that you've found really effective?
No, I wouldn't put much stock in any like Coursera course. There are plenty of good free resources where people at, well-known people at well-known schools just put their lecture materials online. If you can find those are probably fine. I've more often seen slides from people's lectures as opposed to like a full video course, which is unfortunate because that would be a wonderful resource to share with the world. But there was an initial spurt of a full open publication of course materials like MIT OpenCourseWare. But if you look at those, my impression is that almost all of those video lectures that they posted online, again, those are getting on towards like 10 years old now. They haven't been adding new ones. Instead, it's all locked behind paywalls in Coursera. And those courses, I haven't really explored them much myself. They seem like they are structured differently. They're broken into like little 5-minute chunks with quizzes after each 5-minute chunk. It's not designed for someone who's trying to move to the top of the field. Maybe I don't have enough experience. I should probably not besmirch something for which I don't have significant personal knowledge.
And then how about any like inspirational people to check out, like Lex Fridman from MIT. I'm a big fan of his podcast, and he has some super cool stuff related to AI. Is there any people that you look up to in the field, or whose work you find really interesting?
I mean, I certainly have my set of intellectual heroes in the field. Jeff Hinton certainly is at the top of anyone's list in terms of most impactful researchers in machine learning. There's lots of people who have made one or two significant contributions, and Jeff has hit the ball out of the park a number of times, which is astounding over the course of his very long career. But in terms of like podcasts in machine learning that I personally find useful, I think that if you're going to invest your time trying to learn from material, the most valuable material is that which has been very heavily edited in order to make it as rich and clear and accessible as possible. That takes a huge amount of effort, and most of the material that's available out there in the form of something like podcasts doesn't have that level of attention and care invested into it. Textbooks, in the cases where they are timely, I think are an invaluable resource for learning, because that level of attention and effort has been put into digesting the material to the point where it can be absorbed as efficiently as possible. Papers are usually not nearly as good in terms of trying to organize things so that they can be learned efficiently. Particularly within any academic domain, there is a very large base of knowledge that's assumed by any author. And if you are first coming into the domain, you will likely find the papers to be largely unintelligible. When I first started in neuroscience in the beginning of my PhD, reading papers about the hippocampus, there are just all of these different cell types, all of these different regions within the brain, and any paper is going to assume that you basically know them. For the first couple months that I was reading papers, I understood maybe half of what I was reading, and eventually you start to pick up enough that the pieces click together, and you have a richer, more useful reading experience. A textbook is designed so that doesn't happen. A textbook sequences everything so that by the time you get to chapter 5, you have the information necessary to understand it.
Well, thank you very much for taking the time with me today. I really appreciate it, and have a wonderful weekend.
Sure, my pleasure.
Thank you. I hope you enjoyed my conversation with Jason Rolfe. To learn more about him and his work, you can go to variational.ai. And now I'll leave you with the quote from Robert Sapolsky, who among many things is a professor at Stanford. He says, "I love science, and it pains me to think that so many are terrified of the subject, or feel that choosing science means you cannot also choose compassion, or the arts, or to be awed by nature. Science is not meant to cure us of mystery, but to reinvent and reinvigorate it." Thank you.